We now talk about Faraday's law of induction. Now basically the law states that electric current can be induced in a loop by changing the magnetic field. So let us first see figure 1 right here. Now you're moving a magnet into the loop. Now if you're moving the magnet into the loop in this direction, then you are changing the magnetic field passing through the loop. Now if you change the magnetic field passing through the loop, then the current will be induced in the loop. Notice now figure 2. You are moving the magnet now in the opposite direction. That is, you are moving to the right. As you move the magnet to the right, you are again changing the magnetic field passing through the loop. Now this changing magnetic field will cause a current to flow in the loop. Now if you keep the magnet stationary, that is, you do not move the magnet at all, then the flux or the magnetic field passing through the loop does not change. So in this case, the current flowing through the loop is 0. Now we can rewrite this change in magnetic field causing current flow as E equals to minus d phi by dt. So this phi is nothing but the flux which we have talked about before. This is just the line integral of, this is the magnetic field. This is the magnetic field and this is the area vector. So area vector, you know, area vector is always normal to the area and its magnitude is equal to this area A. Now this E is called induced EMF. Now if the coil has n loops, so we have seen just the example of one loop, if there are n loops, then this induced EMF becomes E is equal to minus n times d phi by dt. Again, this phi is nothing but flux, which is defined like this. Now we come to a rectangular loop with an area A. So consider this rectangular loop with area A. So you have a rectangular loop like this. This is the magnetic field which is passing through it. So the area of this loop is A. So this loop has an area. This loop is hollow. I'm just shading it so that you can see it from perspective. So the area of this loop is A. So you have a normal vector which is perpendicular to the loop, and the magnitude of this normal vector is the area of the loop. So you compute the integral. So b vector dot dA vector. So this becomes b dA cos theta. So when you integrate it, you take b and cos theta out. So you have b cos theta integral of dA. So this becomes BA cos theta. So since flux we computed, or we said, was minus d phi by dt. So this phi was the flux. So you get minus d by dt of BA cos theta. So you can see that this electromotive force E, this can be induced if the magnetic field is changing. So if the magnitude of the magnetic field is changing, that is B is the magnitude of B vector, this is changing, or the area is changing, that is the area of the loop is changing, or this angle theta is changing, with time. So we will cover all three of these examples. We will sometimes change the magnetic field, sometimes we will change the area, and sometimes we will change the angle of inclination. Now we consider a quick example. You consider a square coil, and this square coil has side of 10 centimeters. So let us put A side as 10 centimeters, and the coil has 100 turns of wire. Magnetic field is perpendicular to the coil, and therefore it makes an angle 0 with the normal of the coil. Thus cos theta is equal to 1. So notice theta is 0 since we are measuring it with the normal of the coil. Now the field intensity changes linearly from 0 to 0.4 Tesla in 0.8 seconds. So what is now you're changing the field intensity in a given time. So we expect to have some induced EMF. So this induced EMF is given as, so the magnitude of the EMF is N times, instead of d phi by dt, I'm writing delta phi by delta t. So N times, we are using this delta because we have a term linear here. So we could use delta instead of the differential. So you have delta B times A. Now the area is constant. It comes right here out. So we are saying the area is given to you as A square, where A is the side of the square. So you have NA square times delta B by delta T. Now delta B, the field changes from 0 to 0.4. So this is initial value, this is final value. So this is the final value of the field. This is the initial value of the field. So BF minus BI, this will give you 0.4, and this changes in 0.8 seconds. So the change in time is 0.8 seconds. So now you just plug those values here in this formula. So N is given to us as 100, area is 10 centimeters or 0.1 meters, so 0.1 square. This you just write as 0.4 and you have 0.8, and you compute the induced EMF. So you get the induced EMF as 0.5 volts. And recall that EMF is just like a battery, so its units is volts.